Lesson 3.3 is all about basic functions and equations. So we're going to go through and look at different kind of functions or different equations that we've got and what their graphs look like and kind of what that means for us. So first off, some terminology. Origin, the point where the two axes intersect is called the origin. So this spot right here. We can also just call it 0, 0. So this spot in the very middle right at 0, 0, that's called the origin. Now quadrants are the different like corners or different sections of our graph. So this would be quadrant 1, this would be quadrant 2, let me get this out of the way, this is quadrant 3, this is quadrant 4. So if we were to say that we have a line or a graph that goes something like this, we would say that this line happens to be in quadrants 1, 2, and 3, but it's not in quadrant 4. So the quadrants are just the different areas of our graph. So let's look at some specific functions then. Linear functions, we've already worked with these, is a function whose graph is a straight line and can be written in the form y equals mx plus b, where m and b are constants and m does not equal 0. What that means is m and b just aren't variables, they're actual numbers that we're plugging in for those values. And for our purposes, we're not going to have m is 0, so we're not going to use any just like horizontal straight lines. So examples of this would be if you had like y equals 3x minus 4. Okay, and we know how to graph that. We'd start at -4 on the y-axis because this is our y-intercept. We go up 3 over 1 using the slope. Okay, same thing. We could have like 3/4 x plus 8. So 8 would be our y-intercept. Up 3 over 4 or up 3 right 4 would be our slope. One like this, -7x plus 1. 1 is our y-intercept. Down 7 right 1 would be our slope here. And in this one, I wrote it with a plus 0. You could get rid of that 0 and just say y equals 11x. That's still going to be a straight line. It's just going to go right through the origin because that plus 0 means 0 is our y-intercept. Okay, so in a graph like this, if this were our line, technically we would say this is in quadrants 1 and 3. Okay, it doesn't go into this quadrant, doesn't go into this one. It goes right through the origin there. The origin isn't on any quadrant, it's in the exact middle. And we would say for this graph, just this one specifically, not necessarily all of these, but for this one, this example, the domain, D, is all real numbers. We can have any x value on here. I can continue going on this way and get any x values this way. If I go really, really high, like x is 10, that would just be way up here at some point. So I can have any value for x in my domain, and I can have any value for y. So range is all real numbers. I can get a really low number down here. If I was at like at -20, then it would just be way over here. My x value would just be really low. I can have a really tall y value at like 7 or 10 or 20. My x value would just be way over here. So I can get all y's, I can get all x values. Let's look at another function then, the quadratic function. It's a function whose graph is a U-shape, so it looks like this. It's a U-shaped curve that may open up or down. Now this one opens up. You can kind of see that the U makes a little bowl right here. So it may open up or down depending on the sign of the coefficient a, and can be written in the form y equals ax squared plus bx plus c, where a, b, and c are real numbers and a does not equal 0. That's kind of a mouthful. So what that means is I can have something like y equals 2x squared plus 3x plus 8. So my a is 2, b is 3, c is 8. Okay, that would be of this form, ax squared plus bx plus c, with a being a real number, b being a real number, c being a real number, and a, this one right here, isn't 0. If this number was 0, it'd be like we didn't have this thing. Well, that'd just be a linear, just a line then, a linear function, 3x plus 8. But since we do have those in there, that makes it quadratic because we have a x squared term. If there's an x squared term, that's going to make it quadratic, give it this U shape. Now in this example, y equals -3x squared plus 5x minus 4, this is where we would have a a U-shape that goes down, something like this. Because this is negative right here, this graph would go downwards. Okay, but this one, we still have an A, B, and a C, and they're all real numbers, so this one is also quadratic. And then this last one, this is our basic quadratic function. Y equals 1x squared plus 0x plus 1. Well, essentially I can get rid of that 0. We don't need to know that. We don't need to know 0x and get rid of this 1. So really it's just saying y equals x squared. And that's what this graph is here. Y equals x squared. If we're at x is 1, 1 squared is 1. If I'm at x is 2, 2 squared is up here at 4. Same thing. If I go negative 1 squared, so negative 1 times negative 1 is still 1, so I'm up here. Negative 2 times negative 2, or negative 2 squared, it's positive 4. So this graph is of y equals x squared. Now on this graph right here, not every single quadratic graph, but this one, the domain is all real numbers, because I can have any x value that I want that I can plug in. My range, y has to be greater than or equal to 0. The lowest value I can go is 0. I can continue to move up, so I can get up to like y is 10 or y is 20 way up here. I can go pretty darn high, but I can't go any lower than 0. If I take any number and square it, it won't be less than 0. So y has to be greater than or equal to 0. That would be my range. And one last piece of information here. This kind of graph, this U-shape, is called a parabola. So a parabola is a graph of a quadratic function. It's the U-shaped graph. Let's look at a cubic function. We had quadratic, where we had the x squared term. Now we have cubic, so we have an x cubed term. So a cubic equation is a function of the form y equals ax cubed, or to the third power, plus bx squared, plus cx plus d, where a does not equal 0. So as an example, we might have y equals 4x cubed minus 5x squared plus 4x plus 2. Because it has this x cubed term right here, it will be a cubic function. Okay, same thing as we looked at before. This one is kind of our basic cubic function. I can get rid of this 0 here, 0x squared, and we don't need a 1 in front of it. So this would just simply say y equals x cubed. That makes this graph right here. Okay, if I was at 1, 1 cubed is still 1. If I was at 2, well, 2 times 2 times 2, or 2 cubed, would be 8. So it shoots way up here. Well, the difference between cubic and quadratic is that if you cube something, it can go negative. So negative 1 times negative 1 times another negative 1 does go down to negative 1. That's why this kind of takes a turn and goes this way. So at negative 2, we'd actually be down here at negative 8. So this one makes kind of an S-shaped curve. If you want to write that down, remember this one, the cubic function, will make an S shape. And not for all of them, but for this graph right here, this y equals x cubed, the domain is all real numbers, because I can plug any number in for x that I want, and it'll give me a number here. It will exist here. And my range is all real numbers. I can go as low as I want on here, and continuing this way, I can go as high as I want. So the range is all real numbers. Let's look at an absolute value graph. It's any function in the form y equals absolute value of x. And these make V-shaped graphs. Okay, so you'll notice it's like a straight line, comes to a point called a vertex, and continues on the other direction in a straight line, but it kind of like turns right here, makes a little V. So some examples. I can add something to x inside here and say it's y equals absolute value of x plus 2. This would still be a V-shaped graph. It would just start over here instead of right here. I can have y equals 4 times absolute value of x. That just makes it kind of, it's a narrower, a skinnier V shape. Okay, as long as I have this absolute value of x, or an absolute value of something, and x is inside of there, then it will be an absolute value graph. So another example right here, x is inside our absolute value, So y equals the absolute value of x minus 3. That's going to look just like this graph, only it's going to shift down, and at the corner, this vertex is going to start here at 3. Okay? Or I can kind of put each of these pieces together, adding something to x inside of the absolute value, multiplying on the outside, and adding or subtracting on the outside of it. So I can have 5 times the absolute value x minus 2, all of that plus 1. That would also be an absolute value graph. Okay, so all of these will be V-shapes because we have absolute value with x on the inside. Looking at this graph, remember this is just kind of the simple y equals absolute value of x. The domain is all real numbers because I can plug in any value I want for x, but absolute value always is positive. So at least just this piece has to be a positive number. So y has to be greater than or equal to 0. If x is 0, well, the absolute value of 0 is 0. So this is the lowest that I can go. As x gets bigger, though, y gets bigger. As x gets smaller, so as x goes negative, y gets bigger because it's the absolute value of that number. So y can never be lower than 0. So we'd say the range is y is greater than or equal to 0. All right, exponential functions. Okay, this is a function that can be described by an equation of the form y equals a to the power of x, where a is greater than 0 and a also doesn't equal 1. If a equaled 1, well, 1 to any power is just 1, so that would be a straight line. So we won't use 1 to the power of x. So examples would be where y equals 4. So if a does not equal 1, it has to be bigger than 0, we can use things like y equals 4 to the power of x, or y equals 2 to the power of x, all of that plus 1. Or we can use 4 to the power of x, all of that times 2. We can use that, like 4 to the power of x times 2, and add like a minus 4 or plus something on the end of it. Any of those will still make this kind of graph. Now, how this looks is x is going to go as low as we want in this direction, but it's going to get very, very tiny, and it'll approach 0 right here, but it'll never actually touch 0. Okay, we'll never actually have y equaling 0 at this spot. So actually our range, should be greater than 0. So we can use any x value we want, so the range is all real numbers. The y values, everything has to be bigger than 0. They can't be exactly 0. So it just has to be everything above this line. That would be an exponential function. Let's go on to radical functions, functions of the form y equals square root of x. Okay, this type of graph is a curve. It's like a half of a sideways parabola. If we had a parabola right here, and we only had the top half of it. Now, just like before, we can add or multiply to the equation to kind of change it. So some examples of a radical function would be like y equals the square root of x plus 1, or y equals 2 times the square root of x. Or we can put this plus 3 underneath the square root, so the square root of the amount x plus 3. As long as there's this square root with x underneath it somewhere, it would make a radical function like this. So we can have a really big one like this, 5 times the square root of x plus 1, all of that plus 4. Now again, if we're just looking at y equals the square root of x, that would look like this graph. So our domain would be x has to be greater than or equal to 0. Notice how we only have values over here, starting at 0. X can't go negative. You can't get the square root of a negative number. So we can't have any negative numbers for x. Also, the square root of a number can't be a negative. Okay, the square root is always a positive number. So if we had the square root of 0, we would have 0. Square root of, if we are at 1, well, the square root of 1 is 1. So we only use this value for it. The square root of, let's say we are up here at 4, square root of 4 is 2. So it'd be these values along this curve. And we don't use the negative versions, just the positive versions here. So y always has to be bigger than or exactly equal to 0. So this would be our domain and range. One more, we have the reciprocal function. Any function of the form y equals 1 divided by x. Now it doesn't always have to be 1 right here, it's just always something divided by x, or divided by x and some more. So you can add or subtract or multiply to the equation, that's fine. So we can look at things like y equals 1 divided by x and then add 1 at the end of it. Or instead of 1 divided by x, we could do y equals 2 divided by x. Or instead of just dividing by x, we can do 1 divided by x plus 3. Okay, that will still look like this kind of a graph. Or you can make it really complicated and do y equals 3 divided by x plus 7, all of that minus 4. In the end, if we're looking at kind of the basic function, y equals 1 divided by x, it's going to give you kind of these two swoops right here and here. Now, kind of like the exponential function, there's an invisible line right here at 0. Y will never touch that 0. It'll get really, really close on both sides. This side of the line, it's coming down, coming down, coming down, but it will never touch 0. This side of the line, it's going up, going up, going up, but it'll never touch 0. Okay? Same thing with our x value right here. There's an invisible line that will never touch. It'll get really, really close on this side, and coming on this one, it'll get really, really close, but never actually touch 0. Okay, so it'll look like these two swoops. We'd say the domain is all real numbers except 0, because we can't touch 0 on this line, but we can have any other x value. The range is all real numbers except 0, because we can go up and down anywhere we want except this line right here, except where y is 0. So that'd be the domain and range of a reciprocal function. A conjecture is an opinion or theory so formed or expressed, guess or a speculation. So we're going to use a conjecture here and decide what this function might look like. So the steps in graphing different functions are make a table, plot some points, and connect them. And you always want to make sure you use enough points to kind of get a feel for how the graph is going to look. So first off, we're going to make a conjecture and say because this has an x squared, we think it's going to look like a U-shaped graph. It's going to be a quadratic function. So let's plot some points then and actually check them. If I plug in -2 for x, well, -2 squared, so -2 times -2 is 4, plus 1 is 5. If I plug in -1, -1 squared is 1, plus 1 is 2. If I plug in 0, 0 squared is 0, plus 1 is 1. If I plug in 1, 1 squared is 1, plus 1 is 2. And if I plug in 2, 2 squared is 4, plus 1 is 5. So I've got 5 points here. Let's put these on the graph. If I'm at -2, so x is -1, 2, y would be up here at 5. So here is a point. If I'm at -1, right here, I have to go up 2. If I'm at 0 for x, I have to go up 1 for y. If I'm at 1 for x, I have to go up to 2 for y. If I'm at 2 for x, 1, 2, I have to go up 1, 2, 3, 4, 5 for y. So here are my points. I just simply connect them right at this corner. Then it turns around. Oops, kind of missed it there. This is going to kind of continue to go up like this. So this would be the graph of y equals x squared plus 1. Notice it kind of makes that U-shaped graph here. And it has a corner right at this spot. So that would be how to graph the functions. And that'll be it for 3.3.